The Manhattan distance is the sum of the absolute differences between the coordinates of 2 points. It is also called the taxicab distance, as it represents the distance traveled along grid lines. Let us plot a coordinate system where we will visualize 2 points and calculate their Manhattan distance. Here are 2 points, labeled as x1, y1 and x2, y2. In Manhattan distance, we calculate the total distance by following the grid lines. This can be visualized as moving horizontally and vertically to reach the other point. The horizontal segment represents the absolute difference in x coordinates, and the vertical segment represents the absolute difference in y coordinates. The Manhattan distance is the sum of these two distances. Mathematically, it is represented as d equals the absolute difference of x2 and x1, plus the absolute difference of y2 and y1. Now, let's understand the concept of Manhattan distance using the same movie recommendation example. Manhattan distance calculates the distance by summing the absolute differences between corresponding coordinates. To calculate similarity, we compute the Manhattan distance between the new user and each existing user. Let us compute these distances step by step. First, we calculate the Manhattan distance between user 1 and the new user. This is done by summing the absolute differences between their ratings. Next, we compute the Manhattan distance between user 2 and the new user. This results in a total distance of 6. Finally, we calculate the Manhattan distance between user 3 and the new user. The total distance comes out to 9. From these calculations, we observe that user 1 has the smallest Manhattan distance to the new user. This means user 1's preferences are most similar to the new user's preferences. Hence, we can recommend movies that user 1 rated highly, which the new user hasn't watched yet. Manhattan distance has several unique characteristics. It measures the distance between points along axes at right angles, making it suitable for grid-like data or scenarios with distinct dimensions. It is less sensitive to outliers compared to Euclidean distance and performs well in high-dimensional spaces. However, it can overemphasize dimensions with larger scales, so normalization is essential. Manhattan distance finds extensive applications in scenarios with grid-based or discrete data. It is commonly used in pathfinding algorithms like A* for shortest paths in grids, in clustering algorithms like K-medoids, and in recommendation systems where data may be sparse or grid-structured. In this video, we will explore the concept of Euclidean distance. The Euclidean distance is the shortest straight line distance between 2 points in a Cartesian coordinate system. Let us plot the coordinate system where we will visualize 2 points and calculate their Euclidean distance. Here are 2 points, labeled as x1, y1 and x2, y2. Next, we draw a horizontal line and a vertical line to form a right triangle. These lines represent the differences in the x and y coordinates. The hypotenuse of this triangle represents the Euclidean distance. It is the shortest straight line distance between the 2 points. The length of the vertical line is the absolute difference in the y coordinates. And the length of the horizontal line is the absolute difference in the x-coordinates. Using the Pythagorean theorem, the Euclidean distance is calculated as the square root of the sum of the squares of these differences. This is represented by the formula d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. Now, let's dive into an example. Consider a movie recommendation system. We have data from several users who rated different movies. Our goal is to find the user whose preferences are closest to the new user and recommend movies based on that similarity. To calculate similarity, we compute the Euclidean distance between the new user and each existing user. Let's compute these distances step by step. First, we calculate the distance between user 1 and the new user. The formula gives us a distance of 1. Next, we compute the distance between user 2 and the new user. This results in approximately 2.45. Finally, we calculate the distance between user 3 and the new user. The distance comes out to be approximately 4.24. From these calculations, we observe that user 1 has the smallest distance to the new user. This means user 1's preferences are most similar to the new user's preferences. Hence, we can recommend movies that user 1 rated highly, which the new user hasn't watched yet. Euclidean distance has notable characteristics. It is sensitive to the scale of data, works well for continuous numeric features, and is computationally simple. However, it is not robust to noise or high dimensionality and assumes all directions in data space are equally important. Euclidean distance is widely used in various fields. Some of its key applications include k-nearest neighbors for classification, clustering algorithms like k-means, computer vision for pattern matching, and recommender systems to measure user similarity. The Minkowski distance is a generalized distance metric that can adapt to different distance calculations by varying a parameter called p. It includes both Euclidean and Manhattan distances as special cases. The formula for Minkowski distance is given as the pth root of the sum of the absolute differences of the coordinates raised to the power p. It is expressed mathematically as follows. Let us visualize how the Minkowski distance varies for different values of p. We will start by plotting 2 points in a 2D space. Here are the 2 points, labeled as x1, y1 and x2, y2. When p equals 1, the Minkowski distance reduces to the Manhattan distance. It measures the total horizontal and vertical path between the points. When p equals 2, the Minkowski distance becomes the Euclidean distance, which is the shortest straight line path between the points. As the value of p increases further, the Minkowski distance adapts, giving more weight to larger coordinate differences. The Minkowski distance provides a flexible and powerful metric, allowing customization for various data types and applications. Now, let's understand the concept of Minkowski distance using another practical example. We will compute the Minkowski distance between a new user and existing users for varying values of p. To compute Minkowski distance, We calculate the pth root of the sum of the absolute differences between the coordinates raised to the power p. Let us calculate these distances for p equals 1, p equals 2, and p equals 3. First, for p equals 1, the Minkowski distance becomes the Manhattan distance. We calculate the distance between user 1 and the new user. Next, for p equals 2, the Minkowski distance becomes the Euclidean distance. We calculate the distance between user 2 and the new user. Finally, for p equals 3, we emphasize larger differences more strongly. Here, we compute the Minkowski distance between user 3 and the new user. As seen, the Minkowski distance varies depending on the value of p. For smaller p values, all differences contribute more equally, whereas for larger p values, larger differences dominate. This flexibility makes Minkowski distance suitable for various applications. Minkowski distance has versatile characteristics. It is a generalization of Manhattan and Euclidean distances, controlled by a parameter p. It can adapt to various distance metrics depending on the value of p. It becomes Manhattan distance when p equals 1 and Euclidean distance when p equals 2. However, as p increases, it becomes more sensitive to larger differences in dimensions, which may amplify the influence of outliers. Minkowski distance is widely applicable across various domains due to its flexibility. It is commonly used in machine learning algorithms like k-nearest neighbors and clustering methods, as it adapts to the underlying data's properties by tuning the p parameter. It also finds applications in anomaly detection, similarity measurement for diverse datasets, and as a metric in high-dimensional spaces. Let's compare Manhattan, Euclidean, and Minkowski distances. We'll explore their formulas, special cases, sensitivity to outliers, and best use cases. Here is a table summarizing the differences. The formula for Manhattan distance involves summing the absolute differences between coordinates. Euclidean distance, on the other hand, calculates the square root of the sum of squared differences. Minkowski distance generalizes both by introducing a parameter p, allowing flexibility in calculations. For special cases, Manhattan distance corresponds to p equal to 1. Euclidean distance is a specific case where p equals 2. Minkowski distance can take any value of p greater than or equal to 1, making it a versatile metric. Manhattan distance is less sensitive to outliers because it only considers absolute differences. Euclidean distance is more sensitive to outliers as squared differences amplify large deviations. Minkowski distance's sensitivity depends on the value of p, increasing as p becomes larger. Finally, Manhattan distance is well suited for grid-like data or discrete features. Euclidean distance works best for continuous data and spatial measurements. Minkowski distance's versatility makes it useful for datasets with varying characteristics. This concludes the comparison of Manhattan, Euclidean, and Minkowski distances. Thank you. I hope you found this video helpful. If you enjoyed it, please give it a thumbs up, subscribe to the channel, leave a comment, and share it with your friends. Your support means a lot. See you in the next video.